Hey folks, it's your old pal Mr. Roche here, recording a video because I am gone. It is October 3rd, 2025. I will be back at school later today, so feel free to stop by with questions or send me a Schoology message or whatever you need. Make sure you are being polite to Mr. Berlin, who should be here subbing for me. I'm sure he can help you as well, but just know that you can always save any questions for me. We can always wrap this up on Monday if need be. Pretty typical lesson today. We'll go through some notes. We'll get you work time. You should have already completed like a little mini warm-up quiz. This is Unit 3, Lesson 6. We are talking stretches and shrinks. One more warm-up for you on function lands. We're going to be doing a lot of graphing today, a lot of looking at graphs. So just to remind you of some functions we have been working with. I've got these three right here. I'll talk through them here in a second, but if you want, you can pause the video, build a quick mini table, describe the domain and range. We're thinking about what points make sense to graph, right? What is kind of like the reasonable things to want to graph. Yeah, see if you can build those out, and I'll start when you resume. We've got our rational function here on the left. This guy is really only going to have 2 points that we can do. We can do -1, 1, -1 I should say, and we should do +1, 1. It would be a good idea to note that 0 is undefined for us. And then we could also build out a couple more, just kind of show the pattern where when I plug in a number higher than 1, that I'm going to have to graph some sort of fraction. So if you want to build a few of these out, you can. I would say the purple and the orange would definitely be good ones to graph, or at least to have written down. Domain and range for this one, if I draw a quick sketch, this is the two-part function with asymptotes like that. So using our brackets and our parentheses, interval notation, we could start at -infinity on the x-axis and go until 0, and then we jump across that y-axis, and we would start on the positive side of 0 and go to +infinity. That would be working from left to right on my sketch there. Range would be the exact same, except we're working bottom to top. So I start at -infinity and work my way until I hit that first asymptote. And then I jump across and I start working positive until I get to +infinity. That would be the domain and range and the table for the first function there. Next function is our v function. It is our absolute value. This one you don't have to do too much. I think -3 to +3 is plenty. We have that negative slope coming in and the positive slope going out. The only values that we won't see are negative y values. So our domain is from -infinity to infinity. We can plug in any x value. Could also say all real numbers. Our range would start at 0 and infinity, and double check that you used a bracket on that side of it. Last but not least is our square root function. This one for our table, we're going to be strategic and pick out our perfect squares. I could plug in 0 for x, 1 for x, 4 for x, 9. Other than that, it's all going to be irrational decimals that I don't want to deal with, or I'm just going to run out of space. Most likely don't have room for 16. This one, as a sketch of the graph, would look like that. Our domain, 0 to infinity, and our range is the exact same, 0 to infinity. There's your daily problem. Quick warm-up with graphing before we go on. We'll do our trivia question. You can again pause and make your own guess. What Disney princess gets the least amount of screen time in her movie? Hopefully you've paused and thought of a guess. It is Sleeping Beauty. Sleeping Beauty gets the least amount because, she's asleep. Goals today, being able to write and graph equations that are stretched or shrunk. being able to describe the domain and range of a function. I have a little side note that this video is brought to you by Flamin' Hot Cheetos. While they don't actually send me any money, maybe one day they will, or just some, like free Cheetos. So shout out Flamin' Hot Cheetos. Okay. What we've been working on here is trying to model our parent functions a little bit better, right? Because we don't always see this guy in the real world. In fact, I like using the baseball one for stretches and shrinks. It's not like you're always seeing the exact same home run, the same flight path of a ball. You might see some that are like absolute moonshots and go way up into the sky, but then land pretty shallow, if you will, in the stands. And you might see some that are like absolute line drives that get out in a hurry, right? Those ones that really leave the ballpark really fast. And then you have in between, right? Like you hit some upwards of 475 feet that go further, and everything has a different launch angle, different trajectory. Same idea, you can make a roller coaster more fun by stretching it out, right? By making a sharper drop. I think of the SpongeBob ride at Nickelodeon Universe. And then if you wanted to build some sort of wire, this is a really pulled apart parabola, because we need to cover a lot of distance there to connect those two standards. So the idea here is we need to modify our functions even more, which is where we have stretches and shrinks. Now, truth be told, sometimes when I'm typing in stretches and shrink, the I is right next to O. So I accidentally type in shrunk. And then one day I Googled shrunk, and that's what I got. This is also another thing you can prank my sister with next year, is you can only refer to them as shrunks. Like, hey, Mrs. Usher, is this a shrunk? So there you go. A stretch and a shrink is pulling or compressing a graph, making it steeper, making it more extreme, or kind of the opposite, making it less extreme. Our rules stay the exact same. Horizontal happens on the inside, and it's opposite of what you'd think. So if I'm looking at this guy, because it is within our square root function, I know that this 2 is horizontal. To me, it looks like it should be stretching it by a factor of 2. This is actually a shrink of 1/2. So very much like when we see this, we are programmed to say that is right 1. Looks like it should be left 1, but it's right 1. This looks like it should be a stretch of 2. It is a shrunk of 1/2. That is horizontal. Vertical happens on the outside. So this guy, next to our absolute value function, stretches it by a factor of 4. I believe you have this page in your notes. This is like the official, very mathy definition of how this works. When we are inside, right, when I apply the letter P there, if P is greater than 1, if P is above 1, that is going to be a shrink by a factor of 1 over P. It's kind of the opposite. So like this one, P was 2, and this is a shrink of 1/2, 1 over P there. If P is less than 1, it is going to be a stretch by a factor of P. The opposite is true, as we've been talking about for outside. If P is above 1 and P is outside the function, it's going to do exactly what it looks like. It's going to be a stretch by that factor of P. And if P is less than 1, it's going to be a shrink by a factor of 1 over P. So here's a good example to get you started. First one says write an equation, write a new equation for the parent function y is equal to x squared that has been vertically shrunk. So this tells me outside, and this tells me it's going to look quote unquote normal, if you will. So if I have 1/4, I'm going to keep it as 1/4. This new equation would be 1/4 x squared. If you wanted to get real fancy, you could put in some parentheses there to really show that 1/4 is outside of x. This one wants a equation that has been horizontally shrunk, right? So this is going to be inside, and it has to look opposite of what I'd think. So if I'm shrinking by a factor of 5, I'm going to make it look like it's stretched by a factor of 5. That would be your shrink there. Now, one thing that I like to look at here is just some different visuals, right? So I'm looking at the parent function here in red and comparing that to the transformed function in blue. And I think it's nice to see, like, what does a stretch or a shrink look like? You can see that my graph here is being pulled vertically, right? Like if I grabbed here and lifted it up, right, you'd be stretching out this function to get taller. And the other thing that I'd point out is that all of the x values are remaining the same. I have not touched my x values, and my y values have changed. So taking a look at this parent table, I was 1, 1, 4, 2, 9, 3. And my new values over here are 1, 5, 2, 10, and 3, 15. So all of these were stretched by a factor of 5. This is a vertical stretch. It's happening on the y-axis by 5. So I'm on the outside, and I'm going to look normal. If I scroll down, you can see that this one was compressed, right? This one was pressed down. It was kind of squished. I think of those videos that, like, you put like a piggy bank underneath the like giant metal thing that like presses it down and smashes it. Kind of what's happening here. Kind of the same idea too. Like if I'm looking at my values, I go from -1, -1, -2, -2. I'm seeing that -1, +1, -2, +2. There we go. And I'm seeing that my y values haven't changed, but this one has messed with the x values. So my x values are different. And I went from here, and now my x values are 4 times bigger. So I would write it like that. I know you might be saying, well, Mr. Roche, you told me that it was compressed. You told me it was that machine that crushes the piggy bank. It's kind of interesting is that if you pull the x's, it has the same effect as shrinking the y's. It has the exact same effect as pushing those down. And hopefully this doesn't make it too convoluted or anything too crazy. If I look here, another way that I can think about it, this is a 1 and then a y value of 1/4. Another way that I could think of this is instead of stretching the x's, what if I compressed the y's? And it won't work this smoothly for every single function, right? We have some different things going on with square roots and cubes, and it's not always going to be this perfect. But it's kind of interesting that if you mess with the x's, by default, you're messing with the y's as well. So I think both of these equations could work. Based off of the points that I gave you, I was hoping we would see this one. I was hoping you would see this one, is that the listed y values don't change and the x values turn to be 4 times bigger than they were. So I'd put a 1/4 on the inside of the function. Now here we kind of have the opposite, and there's a couple of different ways that you can do this. It's kind of up to you. With some of these more simple or not as transformed functions, I should say, I only have one transformation going on, and that is a 1/4. You can probably just like graph it just by going with the original values that you know. With some that are more complicated, like this one where I have multiple transformations going on, I'm going to do this one with a table. I don't mind if you do a table every time. It's probably like a fail-safe way of doing it. But for this one, I'm just going to kind of talk through my thought process, and then we'll look at tables in a second. If I were to graph this guy, that would be the one that starts at the origin and looks like a snake. So I have 1, 1, I have 2, 8, 3, 27 is probably too big, and then the same thing on the negative side. So I have -1, -1, -2, -8. But this guy has been transformed with a vertical shrink that is outside the function. If it was inside the function, it would look like that, where the third power would apply to that 1/4. But as written, it's a vertical shrink by a factor of 1/4, which really means all my y values are going to be 1/4 as big. So, started the origin here. There's 1 point. Normally, I would go over 1, up 1, but that up is going to be shrunk down. It's going to be compressed to 1/4 its original size. Kind of guesstimating there, but there's my coordinate point, 1, 1/4. It used to be this, and I shrunk the y values by a factor of 1/4. Normally, I would be graphing 2, 8, but I have that y shrink of 1/4. So a fourth of 8 would be 2. And again, just to show you mathematically, this guy gets compressed by a fourth. Now, we really could fit like 27 times 1/4. It's not going to be like the nicest to graph. So I think 2 points going positive is a good start. This one mirrors itself on the negative end of things, right? -1, -1, but this guy is now 1/4 as big. And -2, -8, but this guy is 1/4 as big. And we should see that. And I've got a little tiny compressed version of the snake function. So again, one way you can do this is just like talk yourself through, hey, here's the normal pattern, but the change is the y's are 1/4 as big. I'll do this one with a graph, or a table, I mean. This one I'm going to identify right away. Horizontally, this is stretched. It is opposite on the inside by a factor of 3. So again, I could like do the normal pattern of the square root function, but I like to do this is I like to start with my parent function. So these are the coordinate points I would normally worry about, but I need to horizontally stretch everything by 3. So I'm going to multiply all of my x values here by 3. Y values are untouched. Y values are unchanged. So 0, 1, 2, 3 stay the same. And then I'm going to apply this times 3 one at a time. 0 times 3 is 0. 1 times 3 is 3. 4 times 3 is 12. 9 times 3 is 27. Looks like I won't be able to graph that last point. I like doing it this way because I'm just doing like a really easy multiplication problem a few times. And then I have coordinate points that I can graph. So I have 0, 0. I have 3, 1 would be right there. 12, 2 is getting out there, but I could probably guesstimate to be about right there. And we've taken this square root function and we have stretched it out horizontally. We grabbed the end and we pulled it out kind of like a Laffy Taffy, or I don't know what you kids have for candy these days, but hopefully you get the idea. Now we're getting towards the end. I would like to do this one for sure because it's got multiple transformations. And down here, these are really similar to this guy up here, these two, but it doesn't give you the parent function. So I'll probably go over one of these and just kind of show you how to think through these. But I want to make sure you get some work time today. So I can leave the other stuff and know that there will be a completed notes copy on Schoology if you want to use it. But if I'm looking at this guy, I recognize that this used to be the y equals x squared function. And now 2 things have been done to it. We've got that vertical stretch right here on the outside being multiplied by 2. So I'll give myself a note, a vertical stretch. And then I've got a translation on the inside. Inside is opposite. So this is a left 3. Now it's going to be really hard to try to go point by point and just be like, well, how does this go normally? That is really challenging for me. So this is why I like to use the parent table, and just start making modifications. So my x values are being pushed left 3, which would have the effect of subtracting 3. And my y values are being pulled 2 times higher. So I'm going to multiply all my y values by 2. And the resulting parent table, or I guess the result of the parent table, would be the coordinate points that I graph. So all of the oranges are me subtracting 3, like 1 minus 3 is negative 2, 2 minus 3 is negative 1. All of the blues here are me multiplying the y values by 2. And then, like I said, we've got a resulting point that we can put on our graph. I've got negative 1, 2, 3, 4, 5, comma 8. I've got negative 4, 2, negative 3, 0, negative 2, 2, negative 1, 8. There is my moved function. We took our parent parabola, which looks something like that. We pushed it left 3, and then we pulled it vertically by a factor of 2. Tables for me just help me stay organized. So I'm going to skip over this. I don't think I'm going to record me doing this. Again, I'll put it in the completed notes if you want to see it. I notice a horizontal shrink by 1/2. Inside is opposite. This guy is within my main square operation. But I'm going to finish on this one here. This is really similar to what we did up above, but they don't give us a parent function to work with. So I'm going to kind of build my own parent function, right? I can just see that this is a parabola, and typically a parabola would look like this. It'd have 0, 0, 1, 1, 2, 4, and then negative 1, 1, negative 2, 4. And then I can just start like pulling points off of the new one. I still see 0, 0. So this is the transformed. I still see 0, 0. Now I have 1, comma 2. Which is making me think it's the y's that's being modified. I have 2, comma 8. Again, that might be enough to get me there anyway, but if I just finish this out, I've got negative 1, comma 2, and I've got negative 2, comma 8. I'm noticing that all of my x values here are the exact same, and my y values have been bumped up by a factor of 2. So I'm seeing a vertical stretch by 2, and writing that out would look like that. If you want to be real fancy, did this earlier in the video, you can do that, put parentheses around the x. As long as the 2 stays away from that exponent, it's kind of like a good recap of the difference between that guy and the one that I just went over, that guy, right? 2 is being affected by the exponent. This 2 is not being affected by the exponent. Vertical, not being affected. Horizontal, being affected. Okay, there's one more here that you can go through if you want. I'll put it in the completed notes, but I think I'm going to stop the video here. If I am not back by the end of class, please stop by my room later today. Please bring questions to class on Monday. If I don't see you guys, have a wonderful weekend. Be nice to the sub. Be productive. Get out of class with no homework. Okay, be well. Mr. Roche is out.